হ্যালো।
হ্যাঁ সুজা, কি বলছো? শুনতে পেলাম না।
Good morning to all. Sir, I cannot hear you properly. Could you be louder?
Yes, sir. Please, sir. What are you saying, sir? Already kindly check the YouTube live link.
হ্যাঁ হ্যাঁ, আমি চেক করছি। হ্যাঁ
এই আওয়াজটা একটু কম কম মনে হচ্ছে।
হ্যাঁ, এবার ঠিক আছে।
ঠিক আছে?
হ্যাঁ, ইউটিউব কাজ করছে সুজয়। ইউটিউব কাজ করছে সুজয়।
Okay, okay. ঠিক আছে। So we can start now.
Yes.
So am I audible?
Yes, Sujay, I can hear you properly.
Okay.
No problem.
আর একটু বাড়াতে পারলে ভালো হয়, আওয়াজটা একটু কম আছে কিন্তু।
একটু কম আছে। এবার ঠিক আছে? হ্যালো, চঞ্চল দা,
হ্যাঁ ঠিক আছে, একটু কিরকম একটা স্লো আসছে, কিন্তু এক্স্যাক্টলি আসছে নাকি?
হ্যালো।
হ্যাঁ হ্যাঁ, ঠিক আছে ঠিক আছে ঠিক আছে।
So good morning, everyone. It gives me immense pleasure to announce that Professor Tapon Mondol, Sir, Department of Physics, Vishwabharati University, Shantiniketan, will deliver a lecture on harmonic oscillator and beyond in this morning session. Sir has completed his PhD degree from University of Calcutta in 1993. Sir has achieved many awards and fellowships in his career, such as DST Young Scientist in 1993, UGC Research Award 2009, etc. He was acted as visiting foreign scientist in many countries like Max Planck Institute, Munich, Germany, Lucky University, Czech Republic Institute Physiki, Poland, etc. He has worked as an associate member of different types of national and international academic bodies like Third World Academy of Sciences, Italy, for the period 2012 to 2014, associate of the Institute of Mathematical Sciences for the period January 2001 to December 2003, University of La Plata, Argentina, under TUAS UNESCO program during 2012 to 2014 and 2016 to 2018, 2 times, and etc. His teaching experience is near about 29 years and research experience is about 33 years, and he has completed approx 11 to 12 projects funded by different organizations like UGC, CSR, DST, etc. 6 scholars have obtained their PhD degree and 4 research scholars are pursuing their PhD under the supervision of Professor Mondol. Sir has published approx 76 research papers and 4 book chapters in various peer-reviewed journals and books. Professor Mondol is a regular referee of the scientific journals Physics Letters A, Physics Review, A Modern Physics Letters B, Optics Communications, Pramana, Indian Journal of Physics, and Indian Journal of Pure and Applied Physics. So with this brief introduction, we can say that it's a great honor for us that sir has agreed to deliver a lecture in this webinar. I am requesting to Professor Sapal Mandal, sir, to start his lecture. Sir, please.
Okay. Good morning to you all. Am I audible to everybody?
Yes, sir.
Yeah, is it audible?
Yes, sir.
Yes,
Okay.
yes.
Okay. Thank you very much. So at the very outset, I would like to thank my colleague, Dr. Sujoy Kumar Naik, Department of Mathematics, Netaji Navodaya College, and his colleague for arranging such a wonderful seminar through web. And actually, when I was told by Sujoy that I have to give a seminar to your institution. Actually, I was little bit wondered what to say about. Actually, that time I told Sujay just you put my name and you just put the title like this. You can see that the title is very general. Anyway, I will talk on this title definitely. In any case, actually, this slide, etc., was prepared in a hurried manner. Therefore, I would apologize initially for making the slide very hurriedly. And you know that I will be just a minute how to present. Sujay, just help me here. Present now, okay, and a window, okay. Here is it. Okay, good. Here. Could you see this? Could you see that slide?
Yes, sir.
Okay, no problem. So I will be talking about the harmonic oscillator and beyond. If I delete and beyond the word and beyond, so you are getting harmonic oscillator. Harmonic oscillator is very, very difficult to talk about the harmonic oscillator, and the task is very hard in that sense that I will be trying to sell the ice to the Greenlander, that is to the Eskimos. This is very difficult because everybody knows what the harmonic oscillator is and how the harmonic oscillator are treated and what is the implication of harmonic oscillator, etc. In spite of that, there are a lot of students, and particularly the mathematics, the student with mathematical background, for them I will be talking about this problem from the very basic understanding. Okay, the 1.5 hour lecture will keep you alive with the harmonic oscillator problem and what is going beyond of the harmonic oscillator problem. And it is already Sujay told, and he is very nice of me, nice that he has expressed some good words about me, and it will be difficult to judge. I mean, it will be difficult to give the justice about the words he has already talked about me. Anyway, so the title of the talk is harmonic oscillator and beyond. So what is harmonic oscillator? And harmonic, so we know everyone knows that what is harmonic oscillator. Actually, you know that from Hooke's law that if suppose this is a spring, for example, spring, and this is tied with a fixed wall, and if you stretch the string like this, here I have stretched the string amount of x. In that case, there will be some sort of restoring force. If the restoring force F is suppose the sorry. Yes. So F being the restoring force, that restoring force is proportional to the displacement, and this is known as Hooke's law. So F is proportional to x, that is F equal to some sort of constant into x, that is F equal to k into x. and we have to put minus sign in front of that because of the restoring nature of the force. Suppose if the displacement is make twice of that, so in that case you have to put the force, in fact, double the force. You have to make the double the force. So in other words, the force is proportional to x. If the displacement is double, then you have to make the force also double. Of course, there is a catch, because you cannot have to go, or you cannot go beyond the elastic limit. Therefore, within the elastic limit, the restoring force is proportional to the displacement, and this is exactly what is known as Hooke's law. And this Hooke's law is the basis of the harmonic oscillator problem. Okay, so let me have some very elementary algebra where the harmonic oscillator, how the harmonic oscillator is treated. I must apologize to the expert for patience. So in that case, you know that the force is equal to mass times the acceleration. So this is the force, and this is the acceleration is d square x dt square, because x is being the displacement. So force is nothing but m into acceleration. This is m into d square x dt square. And if I take care the Hooke's law, this force is proportional to x, and therefore I have F is equal to some constant into x. I told you the restoring nature of the force will be considered just by taking a negative sign in front of that. Okay, so F is equal to m equal to so this is the equation of motion of the harmonic oscillator, basically, because I'm talking about the simple harmonic oscillator. By simple harmonic oscillator, we mean that the oscillator with one dimension. So I am talking about the one-dimensional case of the oscillator. Okay, just if you simplify, suppose m is divided by here, so m is going downward. Therefore, d square x dt square will get sign that minus k by m x, and if I put root over k by m is equal to omega square, in that case d square x dt square equal to minus omega square x, and k is the constant which is also known as the force constant, and it has the dimension of force per unit length, because you have the dimension of force here, force, this is the dimension of force, and if you divide it by x, therefore k has the dimension of force per unit length. So k has the dimension of force per unit length, and m being the mass, that is the dimension of gram, and therefore finally the dimension of omega will be 1 by t, that is called the frequency dimension. Anyway, d square x dt square equal to minus omega square x. Since you are from the mathematics background, so you know that this is a second order differential equation. And this is a second order differential equation, and moreover, this is a this is actually a second order differential equation with a constant coefficient, because omega square is a constant quantity for a force constant, for a particular constant k, because k is a constant after all, and m being the mass, therefore omega is a constant quantity, therefore omega square is also a constant. Therefore we have a second order linear differential equation. So second order linear differential equation with constant coefficient, and one can go for the solution it easily. So this is the actually this is a school days problems. So one can go for the solution of the second order differential equation, and the simple differential equation we can go for the solution, and the solution, obviously this is a second order differential equation, therefore we should have two linearly independent solution, and finally we get two linearly independent solution like this, e to the power I omega t and e to the power minus I omega t. These are the two linearly independent solution. Therefore the final solution should be some superposition of two linearly independent solution. In other words, because this is the linear differential equation, therefore superposition principle is quite valid, and therefore the total solution xt is equal to the some constant e to the power I omega t plus this. One can also write in another way. This is after just arranging e to the power I omega t is say cos omega t plus I sin omega t and so on. and e to the power minus I omega t is equal to cos omega t minus I sin omega t. If you arrange it, so you will get a new constant here. So the solution is this solution is also equally valid for this differential equation. So xt equal to c1 cosine omega t plus c2 sin omega t. In other words, we have but one can also choose the solution like this, because one can arrange this solution in another way, just by taking some algebra. So what is the information we are getting? Actually, the solution is obtained in terms of two unknown constants. Here you can see these are the two constants, C1 and C2, these two constants. And one can go for this also. Here are two constants. Here A is constant and phi is constant. Here A is sometimes called amplitude of the simple harmonic oscillator. Anyway, so we have two constants, nothing wrong about it, because since we have it to a second order differential equation, we should end up with two unknown constant, and these two unknown constant has to be determined just by using the boundary condition. One can go for the boundary condition, that is t equal to 0, what will be the position, that is x0, and also what will happen for the velocity, that is velocity is x dot, that is x dot means the single dot, x dot 0, this is the initial velocity. Therefore, if you know the initial velocity and the initial position of the particle, the solution is obtained in an exact manner. Okay, so this is the solution. In other words, the differential equation and hence the equation of motion of the simple harmonic oscillator is completely solvable in terms of the initial condition. And if I go for the little bit algebra, then you can see that if I say this is the expression I want to keep it, and this in that case, A being the amplitude of the harmonic oscillator and phi being the phase. Okay, so you know that the maximum value of x, that is the displacement of the harmonic oscillator, I will call it a maximum displacement, will be the amplitude A, that is the A, or I mean the A can have value plus and minus A, because you know that cosine function can have value maximum value plus 1 and minimum value minus 1. Therefore, x can lie between minus A to plus A, where A being the amplitude. Since I have got the solution of the differential equation and hence the solution of the harmonic oscillator, simple harmonic oscillator, therefore my task is to find out, because we are from the background of physics, we are always interested about the energy of the system. In that case, one can go for the energy. Before I go for the energy, I will talk about something about the representation of the harmonic oscillator. So I already told you that one of the way of writing the solution, x equal to A cosine omega t plus phi, where A is being the amplitude and omega being the frequency of the harmonic oscillator and phi being the phase. And already I told you omega is the frequency which is related with the force constant divided by the mass. Therefore, if we plot it graphically, so maximum amplitude A will be like this, and minimum amplitude, that is minus A. So it will be like this. So it traces a sinusoidal curve like this, because it is a cosine function graph. Okay, maybe I have talked about some sort of phase also. In that case, actually this is the time period, that is the time period is defined by twice pi by omega. These things are already known from our school days. Okay, I just want to tell you about the motion of the periodic motion, because in harmonic oscillator we would expect some sort of periodic motion, because we have already talked about the frequency and the time period t. Therefore, it has some sort of periodic motion. And by the way, I just forgot to mention that I didn't talk about the damping or anharmonicity, etc. I will incorporate later that how the damping and anharmonicity will affect the simple harmonic oscillator. Before that, I am just talking about the simple harmonic oscillator without damping, without anharmonicity, and also without any forcing term. Okay, So this is the periodic motion. Just this is an example of the periodic motion. This is the equilibrium position, that is x0 say, and about the equilibrium position, it is coming back and forth. So this makes it some sort of periodic motion. I can go for another periodic motion which we are very much familiar. That is the simple harmonic, simple pendulum. That is the one-dimensional pendulum. Okay, this is the pendulum. We are mostly habituated in our room. That is the wall clock. In that case, suppose this is the bob. That's the bob with mass m, which technically we call it a very heavy mass, with point mass rather, to be precise. And it is connected with an inextensible thread like this. This is this is a thread, and it is moving like this. It is moving like this. At one time, say the mass is here. Therefore, the force experienced by the mass because of the gravitation, it will be downward mg. And if you resolve this force along this line and perpendicular to this line, so along this line will be mg cos theta, and perpendicular to this line will be mg sin theta. So mg cos theta, this is the opposite direction to the tension on the thread. Therefore, it balances identically. Therefore, only one force we have. This is the direction of the force, and that will make the oscillation of the oscillator. Okay, this mass will move towards this. Okay, so this is very simple, and this is the simple pendulum. This is one-dimensional pendulum, and theta being the angular displacement. Okay, so if I write down the Hooke's law once again, this is the force md square x dt square. So x being the arc length, md square x dt square is equal to mg sin theta, because this force is this force, direction of the force is here. On the other hand, minus mg sin theta. Mg sin theta, this is the thing which is making the oscillation. So md square x dt square equal to minus mg sin theta, where x being the arc length, this is L being the length of the thread. Therefore, x equal to L into angle subtended, L into theta. So if you differentiate it, it will get it m. Sorry, I missed a factor m here. There will be some m this theta. Okay, so the m here is this L will be downwards. Just you put it here, d square x dt square, and m will not be here. Sorry, this m will not be here. So I will be getting d square theta dt square equal to minus g by L sin theta, where g is the gravitational acceleration and L being the length of the pendulum. Sorry, what is that? Okay, length in the pendulum, and theta being the angular displacement of the pendulum. Okay. You know that if theta is very small, say for example, theta is very small, in that case I can approximate sin theta is equal to theta. Therefore, I just m will not be there. Okay, be precise. So d square theta dt square is equal to minus g by L theta. So if I put g by L equal to omega square, in that case I will get back the oscillator equation once again. And here, just before we go further, I just want to tell you a little bit about this. Suppose this is the bob. I mean, this is the bob here, and in that case, I just told you that if theta is small, such that sin theta equal to theta, in that case, it is a simple harmonic oscillator, equation of motion of the simple harmonic oscillator. However, if theta is larger, say where sin theta cannot be approximated as theta, in that case you have to expand sin theta, so you will get theta minus theta cube by factorial 3 or something like that. So you will get some higher order terms. In other words, you will get some extra term here, which will be contributed as the enharmonic term. So basically, whenever we do this type of algebra here, we are using the fact that we do not want to consider the enharmonic term in the simple pendulum model. In that case, one has to assure that theta is very, very small, such that sine theta equal to theta. One more thing just I want to tell you. So in that case, say for example, if this bob is full of sand, for example. Okay, if I tell you that the bob is here and bob is full of sand, and if and a hole is a small hole is there in the bottom of the bob, what will happen? As the ball moves in a simple harmonic motion, what will happen? It will lose the mass because the sand will go out from the hole. So therefore, mass will be changing with time. So a very simple model of the pendulum can be thought of as the simple pendulum with losing mass. In other words, the mass is changing with time. What do you expect from that situation? You will expect that the bob this movement will be slower and slower, and finally it will be slow down completely, because it is getting damping in the system. Therefore, a very simple thing that if you talk about the time dependent mass of the oscillator, in that case the oscillator will be damped. Okay, so in this oscillator, in this very simple example, I can include the damping in the system just by taking care the mass as the time dependent parameter. On the other hand, I can also incorporate the theta is theta larger, such that I have higher order terms. Therefore, we can include enharmonicity as well as the damping in the system. I will talk about this in the later part. However, these things are not palatable for us anyway. Anyway, let us come back to the harmonic oscillator problem again. So I have a very nice equation: d square theta dt square equal to minus g by L theta. So I do not have any problem in getting the solution of this differential equation. Once again, the solution is simple harmonic, so this solution is once again theta equal to a sine omega t, or this is square omega square if you put it, and like this. So this solution is already known, and one can compare the solution again. Okay, now what about the energy? Just I was talking about the energy because you know that whenever we talked about I told you that the oscillator is completely solvable. I mean, the analytical solution of the oscillator is available, and by using the analytical solution, one can go for the energy calculation, because you know that everything can be calculated because we know the position, we know the momentum. And since we know from the basic knowledge of classical mechanics, that if I know the position and if I know the momentum, I mean momentum means the mass multiplied by the velocity, you know. So if I know the position and momentum of the particle initially, I can have all the information about the particle at a later time t, and the complete dynamics of the harmonic oscillator is known. In what sense? That the energy can also be calculated, and the energy is very simple. The energy is equal to half mv square plus half kx square. This is half mv square, means this is the kinetic energy part of the Hamiltonian. That is half mv square plus half kx square. This is the potential energy part of the Hamiltonian. Because you know that I am not going for the detail of the potential energy calculation, but I told you that force is equal to F equal to minus kx. Just if you calculate the work done, so F dot dx is equal to minus kx dx, and you just integrate it. You will get from 0 to x, say for example, limit. So in that case, you will end up with the potential energy, that is the work done against the force will be treated as the potential energy, and finally the potential energy will come out as half kx square. Okay, so this is the potential energy part, half kx square. and the kinetic energy is half mv square. This is the total energy of the system. And why I am demanding that this is the total energy of the system, because I didn't had I didn't consider the damping or nothing. In other words, the system is conservative in nature. In case of conservative system, you know that the total energy is the Hamiltonian of the system. Also, the Hamiltonian is the total energy of the system. Total energy means that the energy is sum of kinetic energy plus the potential energy. This is the kinetic energy part, and this is the potential energy part. Okay. So what will be the, let me calculate the kinetic energy part first. Dx dt is the velocity, and I told you that this is the solution of the solution of the simple harmonic oscillator, that is a cosine omega t plus phi, where a being the amplitude, phi being the phase vector, and a and phi are unknown, which can be calculated from the initial condition. Anyway, I just one has to fix up the initial condition to get back a and phi. Anyway, so if I calculate velocity, it will come out like this, and therefore so therefore E equal to finally it will come out as just little bit algebra, and finally it will come out as E equal to k into a square. You know that a is the basically a is a constant which has to be determined from the boundary condition. K being k being the k being sorry, where is it? Okay, sorry. K being the force constant, I have already talked about. Therefore, energy comes out as E equal to k a square. So total energy is now k into a square. This is a constant quantity. Means that potential energy is a function of x, and kinetic energy is a function of velocity. Therefore, finally, the total energy is not a function of position, not a function of momentum. Rather, it is a constant energy, E equal to k square. Therefore, whenever we talked about the energy of the oscillator, that the total energy is independent of the position as well as the independent of the velocity. So this is E equal to half k square. You know that how we can take care of these two systems together. So suppose if I am here, here the kinetic energy part is there something like this, and potential energy part like this. Therefore, if I add it up, then I will get back my total energy. For example, if I this is the potential maximum, when the maximum potential energy V is there, in that case kinetic energy is 0. Okay, but in such a situation, that total energy should be preserved, that is equal to half k square. So the energy is conserved as well. So this should be obeyed in physics definitely. Therefore, this the basic law of physics retained, that is the total energy is conserved. Okay. Now I was talking about the classical oscillator, and I started from the very beginning, that I started with the Hooke's law. That is, Hooke's law is the restoring, that what I mean by Hooke's law, within the elastic limit, the restoring force is proportional to the displacement. From there, I got the simple harmonic motion, and the corresponding solution is already known. This is basically the classical approach to the harmonic oscillator problem. However, with the advent of quantum mechanics, we know that this simple harmonic oscillator problem is also treated in quantum mechanics in a great manner. And if I talk about the quantum mechanical problem of the harmonic oscillator, in other words, if I talk about the oscillator problem which I want to deal with quantum mechanics, I should be careful because I have two formalism. Of course, both the formalism will lead to the same results. However, we have two formalism depending upon the physical problems. I mean, what type of problem I am talking about and what I want to calculate, depending upon my motivation, I have to use I can use two types of approach in quantum mechanics. One is called the Schrödinger approach, and the other one is called Heisenberg approach. In Schrodinger approach, actually, we normally we calculate the wave function. I mean, the evolution of the wave function. I mean, the evolution of the wave function has to be calculated in the Schrodinger approach by using the so-called Schrodinger equation. I will come later. Schrodinger equation. The other one is the Heisenberg approach, where the evolution of the Heisenberg operator involving the oscillator will be calculated. So these are two different approaches. In one approach, we want to calculate the wave function. The another approach, we want to calculate the operator. I mean, what I mean by the calculate, I mean, this is the evolution of the operator. I mean, and by knowing the operator at a time t equal to 0, I have to calculate the operator at a later time t. So this is I am talking about the evolution of the operator. Similarly, you have to calculate the evolution of the wave function at a later time t if you are adopting the Schrodinger approach. Okay, so in both these approaches, we can go for the solution of the harmonic oscillator. So let me go for the things like this. So this is the title. You know that these slides were prepared by my students. So I'm thankful to him. Whatever he has written, this is this simple harmonic oscillator from the view of quantum mechanics. And actually, you know that by quantum mechanics means that we have to go for the solution of this Schrodinger equation. Here, H psi equal to E psi. This is the Schrodinger equation. Psi being the solution of the Schrodinger equation, H being the Hamiltonian of the system. Obviously, I will be talking about the harmonic oscillator. Therefore, H will be the Hamiltonian of the harmonic oscillator, and E being the energy eigenvalue. Basically, this is an eigenvalue equation. H psi equal to E psi, where E being the eigenvalue, psi being the wave function. So, if I am able to solve that Schrodinger equation, this is the Schrodinger equation. If I am able to solve this Schrodinger equation, I will get the solution psi. And knowing the solution psi, we have some sort of interpretation in quantum mechanics that if I know the wave function psi, we can go for this solution, or we can go for the calculation of the physical parameters. What I mean by the physical parameters? Maybe momentum, maybe angular momentum, maybe energy, maybe something else. So knowing the wave function psi, one can easily calculate everything about the system. Okay. So our purpose is always to solve the Schrodinger equation. Whenever I'm talking about the Schrodinger approach Schrodinger approach of the quantum mechanics. Okay. H psi equal to E psi, H being the operator, Hamiltonian operator. I told you that in case of Hamiltonian, if it is a conservative system, the corresponding energy will be Hamiltonian. Therefore, I have a very simple problem of harmonic oscillator. In that case, the Hamiltonian will be the total energy of the system. Here is the T is the total kinetic energy part, and V being the potential energy part. So we have to fit the Hamiltonian here by calculating T plus V. And T, you know that this H is the Hamiltonian operator. So one has to take care of the operator for representation of the T and V also. And in case of T, in that case Hamiltonian, that is P square by twice M. One has to replace the P, that is the momentum operator, is equal to minus I cross H del X. So just if you go for minus I cross H means this get minus cos H square by T square dx. Sorry. Okay, sorry. What is happening? Okay, sorry, very excuse me. And this is the oops. This is why it is going. Okay, this is the kinetic energy part in terms of operator. Okay. What happened? Okay, sorry. This is the kinetic energy part, P square by twice M. So this is the P square part here, and by twice M. So this is the kinetic energy part, and this is the potential energy part. And if I feed it here, so once again, the corresponding equation reduces to the second order differential equation. Just let me go for, before I go for the solution of this differential equation, sorry, where is my cursor? Okay, here. Suppose if I put h just by combining t and v, I'll get back a differential equation, second order differential equation. And before I go for the solution, I just want to tell you why I am so much interested about the oscillator, harmonic oscillator problem. This is because here is the thing, why do we need simple harmonic oscillator? I just want to read it out. The physical models are always useful for the understanding of basic physics. For example, the model of a simple harmonic oscillator is perhaps the most useful one among them, because in every case we are using the simple harmonic oscillator model. Why? I will tell you later. The application of the model of simple harmonic oscillator is wide, because it ranges from classical mechanics to molecular physics and classical electrodynamics to field theory. Apart from the wide range of application, the SHO, I mean simple harmonic oscillator, that is the one-dimensional oscillator, and its quantum counterpart provide the exact analytical solution. This is also an attractive problem, because in classical as well as in quantum mechanics, the problem of this simple harmonic oscillator is exactly solvable. In spite of the huge application of the simple harmonic oscillator model, it is inadequate when we come across with the real physical situation. I will talk about later. For example, the inclusion of damping, I just told you a little bit about damping, how the damping comes into the model of a simple harmonic oscillator, and anomality in the model of this SHO, which are inevitable for the real physical situation. So why we are studying simple harmonic oscillator? Because it has wide application, because the model is very simple and it offers an exact solution, not only in classical mechanics, but also in quantum mechanics. That is why this model is very much useful in understanding the basic physics as well. And if you just have some algebra, for example, suppose I have a potential function v as a function of x, v as a function of x. If I expand the function in terms of Taylor series, for example, about x equal to 0, in that case, just you have v0 plus x v prime 0 like this, okay, and x square by factorial to v double prime 0, what is known as perhaps Maclaurin series, f of like this fx. So v as a function of x, if you expand, and if you say that it has a minima, for example, is first derivative of the potential vanishes, that is v prime vanishes. In that case, apart from constant, which is v0, and this first term will be x square by 2. This is exactly the potential of a harmonic oscillator. In other words, you can approximate any potential as a harmonic oscillator potential as a leading contribution, and that is why harmonic oscillator problem is so much useful. And we study the problem from our high secondary classes to our PhD course. Okay, so harmonic oscillator you cannot leave the harmonic oscillator behind. It is always with you. Okay, now let me go forward. So this is the quantum mechanical approach. I told you that this is the well-known Schrodinger equation. Obviously, this is a one-dimensional Schrodinger equation, and this is the kinetic energy part of the Hamiltonian, and this is the potential energy part of the Hamiltonian in E to psi x. This is the very well-known Schrodinger equation for the harmonic oscillator problem, because you know that we have put the potential V as this. Where is the cursor? Okay. Here is the V, and if you change the V, for example, in case of hydrogen atom problem, one has to put the potential 1 by R. So depending upon the potential, so this term, the second term in this part will be changed depending upon your physical problem. In case of a harmonic oscillator, this potential is here. In case of a hydrogen atom problem, you have to put 1 by R potential and something like that. So depending upon the physical problem, this will be changed. However, the kinetic energy part remains same. Now, this is a second order differential equation once again. However, unfortunately, the equation is no more an equation with constant coefficient. You can see that equation is with a variable coefficient. Sir, কোথায় যাচ্ছে রে বাবা? কি হচ্ছে? Okay. So this is a second order differential equation. This is a constant thing, no problem. However, this part is a function of x. So this is a differential equation, second order differential equation with variable coefficient, because the coefficient is no more a constant quantity, it is a variable coefficient. So it is very tough to get the solution. But fortunately, this solution can be obtained just by going for some sort of series solution. And because an infinite series solution, we can try for the infinite series solution. Finally, we end up with that the infinite solution, infinite series is not possible. That depending because of some physical condition. What I mean by physical condition, that is the wave function, because boundary condition, nothing else. Boundary condition of on psi you have to apply. That is the real wave function. To make the wave function the real thing, so the derivative of the wave function will go to 0 in the infinity. That is, if x goes to 0, psi will go to 0, as well as d psi dx goes to 0. In order to obey this boundary condition, one has to put some stringent condition of the solution, that the solution will no more an infinite series, but the solution will be a finite one, finite series solution. And the finite series, you know that this is called a polynomial thing. And we finally got the polynomial solution. So finally, we got the final polynomial solution, and on this way, we can restrict the energy also, E also restricted, because to make the infinite series solution to a truncated series, that is the polynomial, we can impose, or we have to obey some sort of condition on E. Okay. And finally, the solution is obtained. This psi nx is equal to this, and n is discrete, because I told you that n is because of the discreteness is coming. Why? Because of the truncated nature of the solution. This discrete nature is coming. Okay. So this is the wave function of the oscillator. And what I mean by n is the number, that is n equal to 0. For example, if you are interested about n equal to 0, what will happen? Psi 0x is equal to some, this is the normalization constant we are talking about. This is the normalization constant. One can easily go for the normalization constant just by evaluating psi star psi dv equal to 1. That is the normalization I have written here also. Okay. So this normalization constant has to be determined from the normalization procedure. Okay. And hn, that is the okay, hn square root of alpha x. Okay, this hn alpha square root of alpha x is called the Hermite polynomial. I told you that the solution will be a series solution, polynomial solution. That polynomial is called Hermite polynomial. So Hermite polynomial, in terms of Hermite polynomial, and e to the power minus alpha x square. I just told you that if I am interested about n equal to 0, so I have got n0, 80 something x, 80 something alpha x, etc. This is equal basically 1. Okay, and e to the power minus alpha x square. So this has the Gaussian nature. Okay, wave function psi 0x. This is sometimes called ground state wave function of the oscillator. So ground state wave function of the oscillator will be this. And suppose if I want to calculate the normalization constant, I have to go for the normalization condition. This is one can go easily, and just by using the properties of the Hermite polynomial, one can easily calculate nn equal to 2 to the power n factorial n square root, of course downward square root alpha pi to the power 4. So if you put it here, so you will get the solution of the Schrodinger equation with harmonic oscillator in terms of Hermite polynomial. So knowing the value of the Hermite polynomial, in other words, knowing the functional form of the Hermite polynomial, one can go for the wave function for n equal to 0, n equal to 1, and n equal to 2, etc. What we achieved? Actually, we got the solutions psi 0, psi 1 like this. And actually, just I want to tell you one more important thing, that this is a constant thing, so it has nothing to do with the x, and e to the power minus alpha x square. So this is a even function of x, means that if x goes to minus x, this will remain same. However, in case of Hermite polynomial, in case of odd things, that is hn alpha square root of x. So suppose if n is odd means n equal to 1, 3, 5, and so on. In that case, the functional, that is hn alpha x will be odd. In other words, the total wave function will be odd if n is odd. If n is even, in that case, the wave function will be even. So the information is that in case of even main, or I mean n, if n is even, in that case wave function will be even, and in case of odd, wave function will be odd. In other words, the wave function has a definite parity. So this is an outcome of the harmonic oscillator solution, that we obtain the solution of the harmonic oscillator with definite parity, in the sense that if n is odd, in that case wave function will be odd. If n is even, in that case wave function will be even, and n is basically discrete. N can have value 0, 1, 2, etc. In case of n equal to 0, we'll call it as ground state wave function, and n equal to 1, this is called the first, you can call it at first excited state, second excited state, and so on. So if I go for the pictorial representation of the wave function, we'll get like this. Here is the energy. Actually, I told you that during the calculation, we'll get the energy like this. That is the energy En equal to n plus half cross h omega. N equal to 0, 1, 2, 3, like this. You know that E0 equal to half cross h omega. That is E0, that is the 0, this is called 0-point energy. 0-point energy is not a zero energy, that is half into cross h omega. This is quite surprising, because in case of classical oscillator, you can have zero energy, because you can have potential energy 0, you can have kinetic energy 0, because you know that I got the energy of the oscillator k into a square. In case of a equal to 0 or k equal, in that case I can make it 0 energy. So in case of classical oscillator, you can choose your position and velocity in such a way that you can put the energy of the oscillator as 0. However, in case of quantum oscillator, you do not have the freedom to make the energy of the oscillator as 0 energy. It will always a lowest energy, possible lowest energy. This is half cos h omega, and this energy is called the 0-point energy, because you cannot go beyond this energy. And there are a lot of physics behind of that. I am not going for this for the explanation of half cross h omega, because in that case one has to go for the quantization of the electromagnetic field, and one can easily identify this is basically coming from the spontaneous emission quantity. So I'm not going from that. I mean, that is the 0-point energy or vacuum field energy. Okay, I'm not going about the detail of these things anyway. However, if n equal to 1, you can see that the energy will be 3 by 2 cross h omega, and 5 by 2, this is E2, and like this. And interestingly, what we are getting, that the gap between two consecutive energy level is equal to cross h omega. Suppose if I want to calculate the gap between this cos h omega, this is the gap cos h omega, it's one. So whenever you are talking about the energy gap between two consecutive levels, you will end up with cos h omega. Okay. So this is very much contrary to your classical concept of energy. What we got in the classical energy, in that case, we got p square by twice m plus half m omega square x square. So in that case, since p and x, these are continuous function, therefore the energy was continuous. However, for a quantum oscillator, the energy is no more a continuous quantity. It is basically a discrete quantity. This is a sharp difference from your classical picture of the harmonic oscillator and the quantum mechanical picture of the harmonic oscillator. In quantum mechanics, yeah, your oscillator energy will be discrete. Not only that, you can make your total energy of the harmonic oscillator in a classical oscillator as zero. However, in case of quantum mechanics, you cannot go beyond your 0 point energy. So there are a lot of differences in the classical and quantum mechanical aspects of harmonic oscillator. I'm talking about the one-dimensional oscillator, and so there are a lot of differences you can see. And however, one thing is clear, that both the classical and quantum harmonic oscillator are exactly solvable analytically. This is a very, very this is a very advantageous position, that both the problems are solvable analytically. Okay. Now I have just for your refreshing, I just want to give you some wave function. That is the ground state wave function is this. This is the first excited state, and like this. So one can go for the graphical representation of this wave function easily. So sorry, the graphical representation of the wave function easily psi 0, psi 1, psi 2, psi 3, and so on and so forth. So one can go for the wave function. And suppose if you are interested about the probability, what will be the probability? Probability means that you have to make it mod square. However, all of them are positive things. So yeah, there is no sense of taking mod square. Just make it square only. So in that case, you will get the probability of getting. For example, psi 0 square x. What I mean by this? This is the probability of getting the harmonic oscillator in its ground state. Similarly, if I calculate psi 1 square x, in that case, it will give you the probability of getting the oscillator in the first excited state, and so on. So one can easily draw a diagram. Okay, so this is the wave function also I have written here. And finally, this is the probability also. I just told you this is the probability, and I have written here probability. Suppose if I go for the pictorial representation, what will happen for that? So in your background, there is the potential function. That is the parabolic potential. You know that this is the harmonic oscillator potential. And in the middle, for n equal to 0, this is your this is your basically probability I have plotted psi 0 square. So this will be Gaussian in nature. So this is the Gaussian. And for n equal to 1, you have double hump picture. And if you have 3 like this, you want to go on. So you will get 20 hump like this. Finally, what you are getting. So this is the probability of getting the particle in the mid position of the harmonic oscillator. Okay, just you follow me.
Hello, sir. I am interrupting you. Sorry. Someone presenting her page.
Sorry.
Don't present your screen.
Sorry. I cannot hear you. Should I continue, Sujay? Sujay, should I continue?
Sir, you can continue.
Okay.
Yes. Yes.
So I'm continuing. If,
Yes, sir.
if there is any question, I can take care later. Okay.
Okay, okay.
N equal to 0, so this is the probability, and like this, and probability of getting the particle in the mid position like this. And here, this is quite surprising. The probability of getting the particle is much higher in the surface of the in the potential surface. Okay, this is the potential surface. This is the potential surface. I mean, this is the potential surface. And if you go higher in that case, the probability of getting the particle towards the surface. And so this is what is known as the, we are basically going from classical quantum mechanics to classical mechanics. We can have a nice pictorial representation. I have taken from internet, so let me have it. Here is this. You know that the classical particle is moving like this. So this is moving through the surface. Okay, classical particle always moves along the surface. However, in case of quantum mechanics, you know that when n is very large, then it will approach towards the surface. So in case of very high value of n, so what is this? Okay, what? Sorry, where is my presentation? Okay, here it is. Okay, could you see this once again? Okay. Now I'm coming to the harmonic oscillator problem once again for a little bit. Actually, I told you that I want to repeat the word. I told you that simple harmonic oscillator problem is exactly solvable analytically, both in quantum and in classical picture. By quantum picture means I already talked about the Schrodinger picture only. I just want to go a little bit with the Heisenberg picture. Before I go for the Heisenberg picture, I just want to refresh you with the classical representation of the harmonic oscillator again. Just for example, harmonic oscillator Hamiltonian is this: p square by twice f half m minus x square. The equation of motion is this. I already talked about. So just I go forward. So this is the thing. Okay, this is the solution. You know, this is the equation of motion. There is nothing wrong in it, and the corresponding solution is this. Earlier, I written the solution a cosine omega t plus phi. Maybe instead of that, I just have used the boundary condition. Boundary condition in order to calculate a and phi, etc. Finally, I got the solution xt equal to x0 and momentum, that is initial position and initial momentum. I told you that this is a second order differential equation. Therefore, the solution is equal to a cosine omega t plus b sine omega t. That's a very simple solution. And then you have to have two boundary conditions in order to get the solution. I mean, that is the solution. Finally, we got the solution. X equal to x0 cosine omega t, t0 by m omega sine omega t. So this is the solution of a classical harmonic oscillator in terms of the initial position and initial momentum. Similarly, the momentum can also be calculated in terms of initial position and momentum. Therefore, the classical oscillator problem is exactly solvable in terms of this. Already I talked about, but I am repeating again just to tell you.
Hello, sir. Your slide is not visible at this moment.
Oh, is it? Oh, sorry. How to visible? How to? So I'm going out and then
screen again.
আচ্ছা,
Please share your screen again.
আমাকে আরেকবার লগইন করতে হবে কি?
না, লগইন না, আরেকবার শেয়ার করতে হবে একদম।
ও, আবার শেয়ার করতে হবে। আচ্ছা, দাঁড়াও এক মিনিট। আমার তাহলে এটা কেটে দিই বরং। আচ্ছা, ঠিক আছে।
হ্যাঁ।
ও, কোথায় যেতে হবে জানো? এইখানটায় যেতে হবে, গিয়ে আচ্ছা শেয়ার করতে হবে আবার না? আচ্ছা, ঠিক আছে।
হ্যাঁ, প্রেজেন্ট নাও।
হ্যাঁ, প্রেজেন্ট নাও করতে হবে আবার। কোথায়? টার্ন অন সেকশন। আচ্ছা, ঠিক আছে, এখানেই আছে ওটা। ঠিক আছে, রিজিউম প্রেজেন্টিং। ওকে, হ্যাঁ, ঠিক আছে, আসছে, ঠিক আছে। ওকে, সরি, আই এম ভেরি সরি।
না, একজন ভুল করে শেয়ার করে দেওয়ার পরই এরকম হলো। তো
আচ্ছা, এবারে কি ভিজিবল
clear now?
এবারে ভিজিবল হয়েছে?
Participants, is it visible now?
ইজ ইট ভিজিবল?
Yes, sir.
Maybe. Maybe.
ঠিক আছে, আচ্ছা,
No, not yet visible.
not yet
Yeah,
visible.
check.
Okay, just a minute.
Yes, sir. It is visible.
I don't know. I can't see. I can see your face only.
There is two options. There is the
আচ্ছা,
option
presenting
for presentation option. Just
হ্যাঁ,
click on it.
এক মিনিট, কিছু কি হলো বলো তো? স্টপ শেয়ারিং। আচ্ছা, না, স্টপ শেয়ারিং তো করবো না, তাহলে কি হলো, একটা গোলমাল হয়ে গেল। ইউআর প্রেজেন্টিং, তো ইউআর প্রেজেন্টিং এ চলে যাচ্ছে।
না, দেখা যাচ্ছে তো ফুললি।
হ্যাঁ,
ওই হ্যাঁ, হ্যাঁ, ইট ইজ,
লাইট দেখা যাচ্ছে কি?
হ্যাঁ, ইটস রিয়েলি ভিজিবল, ইয়েস।
ও, তাহলে ঠিক আছে। আচ্ছা আচ্ছা, আমি ভাবছি কি গোলমাল হয়ে গেছে বোধ। আচ্ছা, ঠিক আছে।
না না না, ঠিকই আছে, ঠিকই আছে।
আচ্ছা আচ্ছা, ওকে, ইটস ভিজিবল। ওকে, ফাইন, গুড, থ্যাংক ইউ। আই এম ভেরি সরি. So I am yet to be equipped with the modern system. Anyway, this is the once again I am repeating because I have already talked about the differential equation involving a harmonic oscillator. So finally, this is the solution in terms of the initial condition. Initial condition by mean the initial position and initial momentum. So this is the classical oscillator solution. Okay. Now I want to go to quantum mechanical picture. By quantum mechanical picture means I just want to go for the Heisenberg picture. In that situation, X, this position, and P, this momentum, will be replaced by their corresponding operator. I told you that in Heisenberg picture, the time evolution of the position and momentum has to be calculated. So what will happen? So we have replaced the canonical position and momentum. I mean, classical canonical position and momentum has to be replaced by their corresponding operator. So let me go for the appropriate substitution. So here I have replaced the position operator and the momentum operator. That is xt. Is the position operator. Position variable is now replaced by the operator. This hat represents the operator. Okay, x0 cosine omega t, p0 sine omega t, m omega, like this. And similarly, pt, this is the momentum operator, and like this. So what we are gaining, actually I started from the solution of the classical harmonic oscillator. Now I just want to have the solution of the quantum mechanical oscillator in Heisenberg picture. To make it, I just told you that you have to replace the canonical position, canonically classical conjugate, canonical position and momentum by their operators. And after replacement, I just went for the calculation of the commutator. This is the commutator X and PT. And surprisingly, not surprisingly, just by going for the calculation, we will end up with x0 and p0. In other words, the position and momentum, that is the commutator of position and momentum, is independent of time. So this is independent of time, and it is fit with I cross H. And this is sometimes called as equal time commutation relation. So what we are doing, that classical position and classical momentum has to be replaced by their corresponding operator and has to be checked for equal time commutation relation. And this is the this type of quantization is called as canonical quantization rule. Basically, one can easily use the canonical quantization rule in order to get in order to have the quantum mechanical equivalent of the classical solution. So in this way we got this solution. Okay, so there is nothing wrong. So everything is now solved in of the classical oscillator, simple harmonic oscillator, in terms of classical mechanics as well as in quantum mechanics, both in Heisenberg picture and in Schrodinger picture. Now, what is beyond? Now, suppose if I use, say for example, here is if this term was not there, for example. Okay, so this is the equation of the harmonic oscillator, because I have used already for the classical oscillator. Now, if you add this term, means that you are adding some sort of term which is proportional to velocity, and this type of additional term is called the forcing term, because you know that I am talking about the forcing term is proportional to velocity, and this b is a constant quantity. So I have a nice second order differential equation, but nothing wrong in getting the solution classical, not a differential equation. And the solution is straightforward. X equal to a to the power minus b twice nt cosine omega t plus phi. Suppose b equal to 0. In that case, a cosine omega t plus phi. Okay. So we will get back our solution of the harmonic oscillator in case of b equal to 0. In other words, if there is no damping at all, we will get back our previous solution. So everything is going right in the right direction. Okay. So if b is non-zero, then the problem is that b, in case of b non-zero, say b is very large, in case of b very large. In that case, exponential function, I have two competitive functions. A is a constant quantity. I have an exponential decaying function because b constant, m constant. So this is a positive quantity. And along with t is a constant positive. So totally it is a negative argument. Okay. E to the power minus something into cosine function. So I have a two competitive function. One is exponential function, the other one is the cosine function. The exponential function is very much dominating over the cosine function, because if I say that this part is very much high, that is, if b is very high for a particular m, in case of b high means that is the damping is very high. In that case, exponential term will dominate and the solution will go to 0, because e to the power minus this. Here is the picture. Here you know that b, for small b, it will oscillate. I mean, this oscillation is damping oscillation, because the amplitude of the oscillation is decreasing very much. On the other hand, if b is large, in that case, the damping is very fast and it decays out. The solution is decays out. It means that the finally x goes to 0 here. Okay. So the damping is if damping is very large, in that case the solution goes to 0. But the one information is we are getting what information? The solution is exactly solvable. It is not a problem. In other words, the classical mechanics is a robust one in order to get the damped oscillator problem. So damped oscillator problem can be solved in an analytical manner, and it gives an exact solution. It gives an exact solution when we talk about classical damped oscillator. Now the question is what to happen for the quantum damped oscillator. Okay. So before I go for the quantum damped oscillator, so there is some example of the oscillation once again. Okay, now I'm coming to the quantum damped oscillator. Before I come to that quantum damped oscillator, I just want to give you the solution in a different form. So this is the differential equation involving damped oscillator. So just before that, I have the equation like this. Okay, b square x z square minus k by m. This is omega square x, and this is 2 gamma. Say b equal to twice gamma, and you make the side change. So you will get back d square x dt square plus 2 gamma x dot plus omega square x. Okay, so that is exactly what I'm using. X double dot plus 2 gamma x dot. Gamma is actually damping constant. Okay, this is proportional to velocity, damping constant. 2 factor is taken because of for our convenience. And here omega is taken as 1 only, just for convenience. Omega is taken as 1, that is the frequency of the oscillator is taken as unity. In other words, we have chosen our unit and dimension in such a way that omega can be 1. Okay, gamma is the mechanical damping, because I have put it as a damping proportional to velocity. This is called the mechanical damping. So I told you just now that in case of mechanical damping, I do not have any problem in tackling the damped oscillator case in classical mechanics. The solution is straightforward, I told you, but in a different manner, I just wrote the solution in this way. Xt, this is the previous solution is also, this is the same way we can write it, but in terms of my initial position and initial velocity, I have written the solution, because you know that once again it is equally valid. That is, this is a second order differential equation. So you have a general solution like like this. Anyway, the solution with two unknown, that two unknown can be fixed up with the boundary condition, that is x0 and x.0. This is very straightforward mathematics, and it is done in our BSc undergraduate classes. Okay, so one can go for the solution and with the initial condition x0 and x.0, that is t equal to 0, x0, that is the initial position, and this is the initial velocity. So I will get back, sorry, ধরুন আমি পরে কথা বলছি, আমি ক্লাসটা নিচ্ছি এখন. So this is the xt, and one can go for the x dot also, that is the x dot, sorry, x dot, one can easily go for the x dot, because if I know x, I can go for x dot. X dot means I can calculate the momentum, but I don't need to calculate momentum, because momentum p equal to m into x dot, since m is equal to 1 also I have chosen, m omega equal to 1, therefore I do not have any difference between the velocity and momentum. Therefore I have to calculate the commutator x and x dot. This is the x means the position, and this is the momentum, because I talked about the unit mass of the oscillator. So x and p basically here. Okay, so I will end up with e to the power minus twice gamma t x0 x dot 0. So it's a big problem. It's a huge problem, because as t goes to t higher, t goes to infinity, for example, the commutator, oh sorry, I have missed a bracket here. Okay, the commutator will go to 0, right hand side will go to 0 as t goes to infinity. In other words, equal time commutation relation does not hold good for damped oscillator case. So in case of damped oscillator, we fail to get the quantum mechanical equivalent of the solution. This is not surprising. This is not a surprising result. Why? Because in case of damping, the quantum mechanics is actually we do not take care the damping in our quantum mechanics classes. Why? Because quantum mechanics deals with the conservative system. In other words, Hamiltonian is a must in the quantum mechanical system, and the Hamiltonian is the total energy of the system if it is conservative in nature. However, in case of damped oscillator, the system is no more a conservative one. That is why we are getting the result where the damped oscillator cannot be quantized. In other words, the damped oscillator problem, cannot be solved quantum mechanically, and this problem is a huge problem. And this type of problem, that is the quantization of the damped oscillator, was taken care in 1948 or something around by Japanese scientists and also the American scientists. It's a hot topic at that time, because how to take care of the damping in our quantum mechanics. Because you know that in classical mechanics, there is no problem in taking care of the damping. However, in quantum mechanics, it is almost impossible to take care of the damping. In that situation, one has to have some new idea. The idea was I'm not going through the whole development. Just I want to give you some flavor, of course, but I'm not going through the development of how this came about. Anyway, damped oscillator. So you have to understand that in case of damped oscillator, the quantum mechanics fails miserably. So how to get? So you know that as long as we are in the simple oscillator problem, it is exactly solvable in classical mechanics as well as in quantum mechanics. However, If you add some small damping constant proportional to velocity, that is mechanical damping, classical damped oscillator problem does not have any problem there. However, in quantum mechanics, it is not possible. So how to solve this problem? Okay, then there is an alternative method. So we talked about the damping, which is proportional to velocity. Rather, we just do not want to use the damping as proportional to velocity. Rather, we want to use a more general damping. You know that I told you when I talked about the simple pendulum. Just I told you that the pendulum will lose the mass. That is the pendulum with full of some sort of sand. If it oscillates, it will lose the sand, and that is why it will lose the mass and it will damp out. In other words, time dependent mass, if the time dependent mass is there in the pendulum, it will behave as a damped oscillator. This concept was utilized. And that is why we started with the Hamiltonian like this: H equal to P square by twice m half m omega square x square. This is the oscillator. This is the Hamiltonian of a damped oscillator. This is the Hamiltonian of an oscillator with time dependent mass and time dependent frequency. Okay, so the only thing that I am adding, that the mass and frequency of the oscillator is no more constant, which is basically the requirement of your simple harmonic oscillator. Just I'm going beyond simple harmonic oscillator. That is, m depends on time, and omega, that is the frequency, also depends on time. Okay, what will happen? Now one can go for the equation of motion just by going for the equation of motion, x dot equal to p by m and p dot equal to this. So if you combine these two equation of motion, so you will end up with the equation of motion like this, xd double dot like this. Okay, suppose if you think of m equal to mt equal to m0 e to the power twice gamma t, what will happen for that? Suppose if I say mt equal to m0 e to the power twice gamma t, so in that case, just you put it here. So 2 gamma will come out and exponential factor will go. So x double dot plus 2 gamma x dot plus omega square. Suppose omega is constant. Now omega square is constant. So you will end up with x double dot plus twice gamma x dot plus omega square x equal to 0. So you are getting the damped oscillator, which looks like a damped oscillator with damping proportional to velocity. Here is I have written. Okay, no problem. Here I have written x double dot like this. Okay, so if the mass is like this, mt equal to m0 e to the power twice gamma t or minus twice gamma t, whatever it is. In case of losing mass, it will be minus twice gamma t. In case of mass is increasing, in that case, m0 equal to e to the power twice gamma t. So we are getting a damped oscillator once again. However, just by taking some intelligent substitution of the mass. Mass is time dependent. However, mass is equal to m0 e to the power twice gamma t. So we end up with this. So just you follow that in case of mechanical damping, we have some sort of problem. So we try to avoid, we are avoiding the mechanical damping directly. So in order, instead of mechanical damping, we are making our mass time dependent. And as a special case, we will get the damping thing. So it is better to go for the solution, and as a special case, we can go for the damped oscillator problem. Okay, that was the exact prescription what we followed later in the quantization problem of the damped oscillator. Okay, so direct quantization of the damped oscillator is not possible. Therefore, we have to make some intelligent parametric substitution so that we are talking about the damped oscillator, but in a different manner in order to have the quantization of the oscillator. Okay. So there is a lot of, because you know the damped oscillator problem is a very rich subject. and you can go for the literature. We have a very rich literature in physics, and one can go for the oscillator with time-dependent mass, time-dependent frequency, and something like that. These people, this is a very well-known paper, very well-known and very cited paper. That is that this in this paper actually they went for the coherent state of the time-dependent harmonic oscillator, and they took the oscillator as the time-dependent frequency. Okay. In other words, I just want to tell you that instead of taking the damping in the system directly, we can take the frequency or the mass as a time-dependent parameter for taking care of the damped oscillator problem. Okay. And actually, I did some algebra also in past, maybe some 20 years ago. Actually, I went for the quantization problem of a driven. Actually, I went for a more general case, a driven harmonic oscillator with time-dependent mass and frequency. In that case, just I want to share with you what I did long back. Actually, you know that this is the equation of motion. Just I told you that this is the equation of motion, and ft, if ft is the what, ft is basically, this is the driven term. Okay, this is the driven term, and m is the mass of the oscillator, and omega being the frequency. Suppose if driven term is not here, this is equal to 0. You will get back your previous equation like this: time dependent mass and time dependent frequency. In case of, just I have substituted here, mt equal to m0 to the power twice gamma t, and omega t equal to omega 0 equal to 1. You will reduces to the damped oscillator problem. Okay, so it is better to solve this problem directly and get the damped oscillator problem as a special case. What are the special case? That is, we have to put mt equal to this, ft equal to this, omega t equal to this. So we are tackling a general problem, and from where I can get back the damped oscillator problem as a special case. So just I want to share with you, I just told you, this is a second order. This is the classical equation. Okay, this is I just want to tell you before I go further. I just want to tell you, this is the differential equation of a damped harmonic oscillator, or whatever if you reserve the term damped, just I can tell you that this is the equation of motion of an oscillator with time dependent mass and time dependent frequency with driven term. Of course, driven term is also time dependent, ft. So this is the equation of motion of an oscillator with time dependent parameters. These parameters are, this is the driven parameter, this is the frequency parameter, this is the mass parameter. Okay, this is a very general equation. This is a very general equation, and one can go for the solution of this problem to get the solution of the classical oscillator with time dependent mass, frequency, and driven term. So that I did. Actually, what is this differential equation tells us? This is a second order differential equation. This is a, I think you are mathematician, still you will face some problem in getting the solution, because you know that I have the differential equation, second order differential equation with time dependent parameters. It's a bad equation indeed. It's a bad equation, definitely. So we went for the solution of this differential equation. So what clues I have? I have second order linear differential equation, of course inhomogeneous, because ft is you can make it in the right hand side, ft, and it is a inhomogeneous second order differential equation with variable coefficient. Every bad things are there. Okay, so we just want to go for the solution. So one can go for the solution easily. So what are the prescription? One can assume the solution like this. So this is the solution, that is in terms of initial position and initial momentum, initial velocity, whatever it is. Xt equal to a1 x0 plus a2 x dot 0 plus a3t. Why A3T is coming? Because inhomogeneity. But if inhomogeneous term is not there, in that case A3 will not be there. Okay. So xt equal to this. This is the solution of the equation. Okay. What is the time now? Okay. So I think I have how much time? I have 12:15. Okay. So 12:15. Okay. Yeah.
Yeah, sir, you can take time.
Okay. Okay. So I'll continue. Okay. Xt equal to this. Then one can xt equal to this, and x dot is obviously, sorry, x dot means momentum. P x dot can be calculated because here is the x, and x dot is what? Is x dot is equal to a1 dot x0, a2 dot x0 dot 0 plus a3 dot. So momentum will be simply m into x dot, m into this. So I've got x, I have got p. Now one can go for the quantization problem, but the problem will remain same, that you cannot quantize the problem. You cannot quantize the equation. I mean, you cannot quantize the oscillator. So direct solution of the oscillator will give you the problem. So what will happen? So the prescription is like that. So since it is a second order differential equation, we know that the second order differential equation has two linearly independent solutions. Rather, here is the direct solution we chosen. Okay, here is the direct solution we have chosen in terms of initial position and initial momentum. However, we are not going for the direct solution because direct solution has a problem, because you cannot quantize. And in that situation, we are going for the properties of the differential equation. And the properties of the differential equation is used, that is x1 and x2. These are the two linearly independent solutions. So finally, the solution will be the combination of two linearly independent solutions, plus this solution is coming because of the inhomogeneous nature of the solution. So linearly independent solution will satisfy the homogeneous part of the solution. This is the homogeneous part of the solution will be satisfied by the linearly independent solution x1 and x2. This is very straightforward mathematical algebra. Okay, this is very straightforward algebra. X1 will satisfy the differential equation. This is the differential equation, you know. This is the differential equation, the homogeneous part of the differential equation. Ft is not here. So x1 double dot m dot by am plus omega square, etc., etc. Omega square, this is that. X1 double dot m dot m, this. So x1 and x2, these are the two linearly independent solutions. Therefore, they will satisfy the homogeneous part of the differential equation. And particular solution will satisfy the other one, xp double dot equal to this. Now, this C1 and C2, these are the expansion coefficient. Sorry, I missed it. Okay. C1 and C2 has to be evaluated. So, what are the problem? Now, C1, C2 has to be evaluated. C1, if I am able to calculate C1, C2, and of course, the linearly independent solution, then I will be able to get my that solution. So prescription is like that. So I have to get C1 and C2, then I have to go for the linearly independent solution x1 and x2. First, I want to go for the solution C1, C2. How to get my C1, C2 solution? Now C1, C2 solution, so x0, say for example, x0 is equal to what? C1, x1, 0, C2, x2, 0, xp0. And x dot 0 means C1, x1 dot 0, C2, x2 dot 0, xp0. So I have two simultaneous equation involving C1 and C2. So C1 and C2 calculated just by algebraic method. So C1, C2 is calculated. Okay, C1, C2 is now calculated, and therefore C1, C2 is calculated, and in the meantime we have got the Wronskian of the solution, because this is the Wronskian of the solution. You know that x1, x2 dot, because these are the two linearly independent solution, x1 and x2. Therefore, we have Wronskian Wt equal to this, mt x2 this, and Wronskian here it is depend on time. However, if you take the differentiation dw dt, you will find that dw dt is 0. Therefore, Wronskian vanishes. This is the property of the Wronskian. There is nothing wrong in it. So this is the Wronskian of the solution, okay, WT. Now knowing the C1 and C2, C1, C2, so I have the solution, and here C1, C2, after putting C1, C2, and C1, C2, since C1, C2 is known in terms of x0, x dot 0, etc. So finally we rearrange xt in terms of x0, x dot 0, and then we compare our previous solution. So in that case, I will get back A1, A2, A3 just by comparison. Just by comparison, we get A1, A1 this, A1 this, and A2 this. Okay, and A3 also this. So after getting A1 and A2, A3, so I have the usual solution. Okay, I have the usual solution. X equal to this, A1, A2, A3 is known, and X dot is also known. Therefore, the solution is obtained. Now I can go for the permutation relation. XTPT, now we are getting MT by M0 like this. Finally, A1, A2 dot minus A2, A1 dot. One has to calculate A1, A2 because A1, A2 already known. And therefore, finally we got this Wronskian is time independent. And the goal is achieved. In other words, the oscillator with time dependent mass and time dependent frequency does have quantum mechanical solution. Okay, so this is the way. Now in very recently I have made some contribution in this field also, that if you are interested you can go for the paper that is published in 17. So this is the classical and quantum harmonic oscillator with time dependent mass and frequency, a new class of exactly solvable model. Actually I gave some sort of stringent condition by which the model could be solved in an exact manner. I'm not going through the detail of this, but just for your curiosity, I'm giving these references for your. If you want, you can go for. Now, just I told you that oscillator with damping. What is the problem? And I just talked about the damping of the oscillator could be tackled just by using the mass or frequency as time dependent parameters. Now recall, if sine theta is not equal to theta, in that case the corresponding oscillator will be called as anharmonic oscillator. Anharmonic oscillator means that you have some anharmonic term. An anharmonic term is really a term which does not give us peace in our mind, because the anharmonic term, when there is some sort of anharmonic term, the problem is no more exactly solvable. Either you have to go for I mean what I call the approximate solution and something like that. Not only that, every time you have to check about the I mean what is called that is the validity of the solution. That is the solution does not blow up. That is what is in mathematical term. That is the suitability. Okay, just I forgot the term anyway. We have to check the validity of the solution. Okay, just for your refreshing, I just want to tell you that paper actually I tackled little bit earlier, maybe more than 20 years ago. This is a problem which I solved in my early stage of my career. This is the quantum oscillator problem. You know that this is the term lambda into x cube. Here is lambda into x cube. If this term is not there, so this is the harmonic oscillator problem. But if this term is there, this is no more harmonic oscillator, but anharmonic oscillator. And this term is sitting here will give you a lot of troubles, because the solution may diverge because of this lambda x cube. Even lambda, even if lambda is small, the solution may diverge. And there are a lot of problems involving the anharmonic oscillator business. Okay, I'm not going through the detail of this, but I just want to share what I did long back. Here is the solution I tried with the help of Taylor series method. Okay, it looks very mathematically complicated. This is the Taylor series method. Xt is the solution, assuming the time is short. Because if you go for a long time, the solution will diverge. And there are a lot of ways of taking care of the divergent nature of the solution. I'm not going through these things because one has to take care of the summability condition and something like this. Anyway, I'm not going for that. I'm just going for the straightforward solution. I mean, just by using the Taylor series method. And this Taylor series method gives you finally the solution like this. It's not a good looking solution after all. X equal to x0, what they say. Apart from that, if lambda equal to 0, this is the solution of the harmonic oscillator part. But lambda is not equal to 0, we are getting a huge complicated solutions. Okay, and this is only for linear part of lambda, and there are a lot of higher order terms of lambda. So you can imagine what is the problem behind the enharmonic oscillator. So unfortunately, I tackled this bad terms in a nice form. Actually, this was tackled with the help of difference equation. You know that we constructed the difference equation, and finally we are able to get the solution of this differential equation. Here also differential equation with variable coefficient, and this is also not a good algebra, but one can go for the algebra and can tackle the solution. And finally, we got a very nice solution. X equal to this. This is the quantum mechanical solution, of course, and this is the solution we got. Of course, linear in lambda. And with this, actually, we got the solution, and it got published. And later on, actually, this solution was used in various physical problems. Actually, upon this solution, at least 2 of my students have got PhD for different type of problems. You know that it's a huge achievement in some sense, because this type of solution was not there at that time. Anyway, so I just talked about what I talked about the harmonic oscillator problem, and I went beyond the harmonic oscillator problem just by taking care the damping in the system. And also I took the enharmonicity in the system. There might be some sort of forcing in the term, forcing combination, but I didn't went for the forcing term because I think my time is almost over. And also I didn't took combine. I mean, I didn't took damping and enharmonicity combined because it will make our life I mean, full of complexity. Anyway, this type of problem we are tackling nowadays. And with these things, I must stop here. And I am thankful to you for your kind presence. And I just want once again thank you, thank Sujoy for invitation. And I am thankful to my student who made this slide for my presentation. Thank you very much. Okay, Sujoy, I'm stopping here.
Sir. Sir. Thank you very much, sir, for this wonderful lecture.
So
Now the question hour session is open. Participants are requested. If you have any question, you can ask sir directly. If you have any question, you can put it in the chat box also.
Sujoy, maybe it is too elementary to ask questions or
There is no question. There is a question.
Okay, just tell
from
me.
Bapon Goala. He is
What is the
asking
question? Could you tell me the question? I am just not.
for simple harmonic oscillator,
Sorry, Sriya, let me, please repeat again.
For simple harmonic oscillator,
Yes.
photon energy En E suffix n equal to n plus 1 by 2 h omega for n number of photon.
Yes.
If there is place where no photon existed, then n equal to 0. There is no photon, but from equation energy En equal to half h square omega.
Yes.
Please explain no photon, no oscillator. How there can be energy in mere vacuum?
No, actually, I do not know who asked this question, because this question is basically half cos h omega is still there. This is called 0-point energy, and this is called vacuum field energy. Unless you go for the quantization of the electromagnetic field, you cannot have the answer. Because if you quantize the electromagnetic field, you will get back your n plus half cos h omega once again. If the frequency of the field is monochromatic frequency. I just repeat again. For monochromatic field, field with frequency omega, the corresponding energy will be n plus half h omega. Then in case of n equal to 0, he has asked n equal to 0. In that case, there will be no photons at all. But this is called zero field. Zero field still it has energy, and this energy is responsible because of the spontaneous emission. Actually, I didn't wait much for this thing, because it requires the quantization of the electromagnetic field. Unless I quantize the electromagnetic field, it is very difficult to answer this point. However, I am thankful to the participant for this question, because it is definitely it should be the question like this. But I am unable right now to answer this question at this stage. Just I can tell you that in case of quantum mechanics, the 0-point energy is not zero, because of some you can explain it in terms of uncertainty relation also. But it is better to answer in terms of the field theory. But how is it going? সুজয়, বলা মুশকিল এখানে, বুঝেছো? এর চেয়ে কিছু বলা মুশকিল, কারণ এর চেয়ে বেশি কিছু বলতে গেলে আমাকে অনেকটা কিছু বলতে হয়। আমি ভেরি সরি।
Hello, sir. Sir, I am Shantanu Mandal. I have a question. Sir, you have told that, sir, I am Shantanu Mandal. Sir, you have told that we cannot introduce damping directly in quantum oscillator case, since it is damping is basically a dissipative force. Therefore, the system will not be conserved anymore. Okay, but one of your slide, I find that the commutation relation that is time dependent, that is commutation relation between xt and pt, it is equals to some term of damping times the commutation relation at time 0.
Yes.
Okay.
Minus gamma t or 0 to 0.
Yes. I have set two questions. The first one is, can we write that equation, because we don't know how should we damp quantum oscillator case. My question is basically on e to the power minus 2 gamma t. Can we write that form?
Yes. Okay. Just we are trying to quantize canonical quantization, because you know that just from analogy.
Yes, we have just introduced this from analogy from classical case. Yes.
And then we failed. So then we can conclude that this is not the procedure of getting the quantized form of the oscillator. So we failed.
Yes, sir. Yes, sir. That we can say that. Yes, sir. That we can see that after a huge time that this commutation relation will be 0. I think this is the answer.
Yes, and you have already answered. Because why we failed? Because the damping cannot be treated in quantum mechanics.
Okay. So my next question is, to tackle this, I think you have introduced just mass is dependent on time.
Yes.
and frequency is dependent of time. So I don't understand how can we tackle this problem damping in this manner actually. Uh,
Just I told you that suppose I have a bucket of water, okay,
okay,
and
okay,
the bucket is there is a small hole at the bottom of the bucket, and the bucket is
okay,
now hanging like a oscillator, and just it is oscillating, and it will lose water with the time,
okay,
and therefore it will damp out, because you know that as the mass is losing, okay, and the omega will also time dependent, because omega equal to square root of k by m. Since m is time dependent, omega will also be time dependent,
time dependent.
and
Okay, okay,
therefore
okay,
you can think of how the time dependent mass and frequency will become.
okay, sir. I understand. Thank you, sir. Thank you, thank you, sir.
Okay. Continue.
Sujay, has there any question?
Uh, any other question? No, I think there is no question. So I'm requesting to Dr. Chancellor Gora to say something or share his
Sujay,
thoughts about it.
has there any question?
No. I think there is no question. You can proceed.
Okay. I think this lecture is both informative and fruitful. Fruitful for the researchers and mathematicians who are working in this field. So on the behalf of the Netaji Nagar Day College, I thank Dr. Shopan Mundal of Vishwabharati for his wonderful and encouraging lectures. I think all are benefited from this lecture. Thank you, Professor Mundal.
Thank you, sir.
Okay.
Thank you, sir. Thank you very much. You have spent a lot of time for us. Thank you.
Thank you, Sujay, and your team also. Okay.
Thank
I'm going
Okay,
off.
thank you.
Okay.
you.
Okay.
Okay.
Thank you, thank you.
The participants, we shall meet at 2:30 p.m. Where 4 scholars will present their papers. So I am requesting you to join that session at 2:20 p.m. Okay, thank you.